Welcome to the Chemistry, Biology, and Math Revision Hub. Today we are discussing the Pearson Edexcel International A level Chemistry Unit 5, Section A for January 20 and 21. I will put the link in the description box to the videos of Section B as well as Section C of this paper. Please do not forget to look them up. So let's begin. So Section A, the first question says, when an alkene is added to a solution of potassium manganate 7, the purple solution turns colorless. In terms of electron transfer and oxidation number, how does the manganese change in this reaction? So I wrote for you a reaction that occurs here. Remember, this is 5, those are 5 electrons. So the manganate 7 has oxidation state plus 7 here, plus 7. And then 5 electrons are going to be gained. The other side, we get manganese 2. So it gains electrons, manganate 7 gains electrons, and the oxidation state decreases from plus 7 to plus 2. As we can see, this is going to be the answer, which is part B here. This is the answer. I will continue to the next question. It says, the standard hydrogen electrode uses an electrode of platinum coated in a finely divided form of the metal called platinum black. This is very important, finely divided. So they say, what is the purpose of using this coating? Every time there is a reaction taking place on a specific surface, if there is a smaller surface, there is a division or using very tiny particles, it means you're trying to increase the surface area. So it means the finely divided version of platinum black is helping. When you use platinum, finely divided form of the metal, platinum black, it's to increase the surface area so that the reaction can proceed faster. So they say, what is the purpose of this coating? It increases the rate of equilibrium between the hydrogen gas and the hydrogen ions. As we can see, this is going to be part A. That is the equilibrium you're trying to establish. So I will go on to question 3. Question 3 says, an electrochemical cell is set up to measure the ether cell for the reaction. Here we have the reaction taking place. As you guys can see, iron is being oxidized and tin is being reduced. So this is a redox reaction. And you remember from my previous videos, or if you've seen some of the other papers, we usually put the cell that is being oxidized, or the half cell being oxidized, is always going to be on the left. You can see left-hand side because it's being oxidized. And on the other hand, the one that is going to be reduced because it's gaining electrons, electrons generated from the left side move to the right side to be received. So the one that is being reduced or gaining electrons is going to be on the right-hand side. So here they want us to choose which one is the perfect cell diagram. Now here we do not need to use any platinum since we have the metals and their ions, so that is good. So we need to make sure iron solid is going to be farthest because the most oxidized version is always closest to the salt bridge. So it should be iron solid at the farthest. Then there is a line to separate the phase between the solid and an aqueous. So iron solid, a phase separator, then iron 2 plus, those are the ions. Since in this half cell, this is the most oxidized version, is going to be closer to the salt bridge. Then on the other side, in the other half cell, this is the most oxidized version, is going to be closer to the salt bridge, and then a division between this aqueous state as well as the solid state. So you can see that is going to be perfect. So the answer for this should be a C because it fits whatever we have drawn here. And again, the key thing to understanding this is whatever becomes oxidized, its half cell should be on the left, and whatever becomes reduced, its half cell should be on the right. And when you're positioning the two half cells, the most oxidized version should be closest to the salt bridge. As you see, this is the salt bridge. That is the most oxidized version in this half cell, and that is the most oxidized version in that other half cell. So here you'll get it correct if you follow those rules. Then the next part says, the standard electrode potential for the iron 2 electrode system is that, and the ether cell for the reaction is that. They say, what is the standard electrode potential for the other half cell? Remember, we have established that the tin 2 is going to be on the right-hand side. So since you remember this equation, E theta for the cell should be for the electrode potential for the right-hand half cell minus that of the left-hand half cell. Since we have this, I just fit in. So that should equal to whatever we're looking for minus whatever we have, which is negative 0.44. And when we make this the subject, the answer comes out as negative 0.14 volts. And that is the answer. So let's continue on to question 4. Question 4. Hydrogen-oxygen fuel cells can operate in acidic or alkaline conditions. What is the reaction at the anode in an alkaline hydrogen-oxygen fuel cell? So we are looking at the anode. Remember, I don't know if you guys remember this. Anox. Sorry, let me put that back. Anox. Red cat. So oxidation always occurs at the anode. So we have to look at which one is being oxidized. Remember, in alkaline, there should be OH ions. In acidic, there is no necessity. Acidic oxidation occurs. Hydrogen is going to be oxidized, producing hydrogen ions as well as electrons. But in the alkaline, hydrogen is going to interact with hydroxide ions. So it should be a D. That is what occurs. So let's continue to question 5. It says, which of these has the greatest number of unpaired electrons in each of its atoms? So for me, I drew all the all the shells basically, the configurations for each. So here we have chromium. Chromium has 24 electrons in total. So it means they are going to be for S1, and then that. Remember, this electron here, the 4s had paired in the previous atom. However, in chromium, the second electron shifts to the 5th d orbital. So in iron, we have this configuration here. So here we have pairing. And then for manganese with 25 electrons, we can see there are 5 non-paired. Vanadium, we see only 3 non-paired. So as you can see, chromium is going to have 6 unpaired electrons. All the d orbitals, in the d orbitals, they have 1 electron. So they're all unpaired, as well as the 4s being unpaired. So the answer comes to A. Question 6 says, nickel is classified as a transition metal. This is because nickel, to be classified as a transition metal, you should be able to form stable ions that have partially filled the orbitals. That is the key thing, because a metal that causes the transition of electrons from the when the ligands separate or split up the d orbitals, electrons should be able to transition so that color can be observable. So if that is not possible, it means you do not that specific metal ion does not have partially filled the orbitals. So the key thing is to know the ion should be stable. That is very important. And then that stable ion should have partially filled the orbitals. So the answer here should be a C. Let's go to question 7. Question 7 says, platinum forms a complex with the formula Pt, NH3, 2, and Cl2, and chromium forms a complex with this. So they say, what are the shapes of these complexes? So the key thing we need to know here is any complex you see containing chloride, at least for your level, it should be, at least it has only 4 ligands. And in this case, chromium is going to be tetrahedral. Remember, in your syllabus, you do not study about square planar complexes in detail, or they do not require, in the new syllabus, they do not require you to know the greater details of how these complexes are, except with cisplatin and transplatin, the rest is not required. So here you can comfortably say that this is going to be tetrahedral in that form. And then when we go, again, this is chromium 3, yep. And then when we go to the other complex here, we can see it could be square planar, either cis or transplatin. It doesn't matter, but it's going to be square planar. And again, you study this, it's present in your textbook. So the only possible answer is D, where they say this one here is going to be square planar, while that is going to be tetrahedral. So let's continue to B. B says, what is the bonding between the ligands and the central atom in these complexes? The bonding between the ligands and the central metal atom. So we have to know what type of, these are dative covalent bonds. So both complexes have dative covalent bonds. Bonding between the ligands, here again they say the bonding between the ligands and the central metal. That can never be ionic. It should be only dative covalent bond. So the answer should be a B. This is quite easy actually. Question 8 says, copper chloride is used as a test for the presence of water. I hope you guys remember that. Actually, it should be anhydrous copper chloride. You cannot just use any copper chloride. Then they say this test depends on the fact that, come on, anhydrous copper chloride is blue, anhydrated cobalt 2 chloride is pink. This is correct. Anhydrous is blue, Hydrated is pink. So the answer should be A. That is a fact. So I will go to the next part. Question 9 says, iodide ions are oxidized by peroxidized sulfate ions in aqueous solution. Again, in this case, you remember previously we've discussed this in a previous past paper where we said this and that are both negatively charged, so they're going to be repelling each other. So we usually use either ion 2 or ion 3 in order to cause the reaction to proceed faster. Ion 2 or ion 3 can be used as a catalyst. Now, in this case, if we use ion 2, you can see here it's going to react with the peroxidized sulfate, converting it into sulfate and producing ion 3. Then the produced ion 3 is going to react with the iodide, producing iodine. Let me put a 2 here to make everything balanced. So here the question is asking us, this reaction is catalyzed by ion 2 ions in solution. This catalyst is effective because ion 2 can be oxidized in the first step, and then it can be reduced. Yes, actually, this is a good way to reason why some transition metal ions act as catalysts, because they can be either oxidized or reduced. So the answer here should be a D. Question 10 says that the delocalized electrons in benzene result from the overlap of p orbitals. So the p orbitals do form pi bonds. P orbitals do overlap and they form pi bonds. And again, to remind you, you remember there is this end-on overlap, there is the sideways overlap. So this is going to be a sideways overlap, which forms a pi bond. This forms sigma, and then that with that also forms sigma. So this is the pi bond sideways overlap. That is D. So 10 should be a D. And then 11 says, I put a star on this because it's kind of, you have to think deeper. The reaction of ethene with bromine occurs under normal laboratory conditions, but the reaction of benzene with bromine to form bromobenzene requires heat and the presence of a catalyst. So they say the best explanation for the difference in reactivity is that delocalized electrons in benzene. The delocalized electrons kind of create a higher stability. They create stability. So here there is a kinetic barrier. It means the benzene is more stable due to delocalization. So a result, there is going to be a kinetic barrier that is, so the intermediate is going to be formed before the product can be formed, basically. So I put some extra explanation. You can see here the reactants and the product, there is going to be an intermediate form, that kinetic barrier. So this is going to be formed to prevent basically the reactant to be converted into products is this. So that is why when this question asked, reaction of ethene with bromine occurs under normal conditions, but with bromine we need to heat. That kinetic barrier causes, or due to the stability of benzene, the kinetic barrier requires the reaction to proceed at a little bit higher temperature. Let's go to question 12. Question 12, what is the name of the compound shown? So let me first erase away this. Let's see. So the name of this compound, I usually like to position the carbons. Now, since this one here is a functional group as well as that part, the whole thing basically like that, creating the amide. Again, let me erase that. So I chose to, let me take away this one, just a minute. So the carbon, I chose to call this carbon 1, that is carbon 2, carbon 3, and carbon 4. And we can name, since we know this is an amide, we will count carbon 1, carbon 2, carbon 3, and carbon 4. So it's going to be butanamide. And then there is a methyl on carbon 2. So we can say 2-methyl butanamide. This is a methyl group. These are 4 carbons in an amide. So we say butanamide. So this methyl is on carbon 2. We said 2-methyl butanamide. That is why that is the answer. Question 13 says, separate 0.1 mole per decimeter cubed aqueous solution of ammonia, butylamine, and phenylamine were prepared. Which of the following sequence shows the solution in order of increasing pH? Increasing pH means increasing basic nature. So which one is a greater base? The greater base should be at the end, and the weakest base should be at the beginning. Remember here we are looking at ammonia. Let me show you just a minute. Ammonia should look like that. I'm not drawing the real 3D structure, so bear with me. Butylamine, let me see, it's going to be R. Let me erase and just do the whole thing. So CH3, CH2, 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 NH2. And phenylamine is going to be like that. Let's position the NH2 here. So remember, they all have a lone pair here. I'm going to position this down here so that you can see it clearly. So they all have a lone pair there, a lone pair there. Now this one here, this structure here is going to be the strongest base because there is inductive effect due to having an alkyl group. So there is electron donation from this side, and therefore there is going to be increase in the ability, or there is a greater chance of this lone pair being donated. So this is going to be the strongest base. Now here nitrogen, the nitrogen here has a lone pair, so this is going to be the next, because this actually is a greater base than that. The reason as to why this is not a great base, or its basicity is not that high, it's because this lone pair gets incorporated into the ring and therefore kind of unavailable due to its delocalization within the pi electron cloud, and therefore this is not going to be readily available for the reaction to occur. So it's going to be the weakest base, or the one with the lowest pH among the three. So I said, because they're talking about increasing pH, phenylamine will have the lowest, then we go to ammonia, and finally butylamine. So I think that makes sense. So let's go to the next part. Question 14 asks, the repeat unit of a polymer is shown. So they ask, what is the structure of the monomer? Now we know if you're talking about a polymer and this is a repeat unit, it means the double bond must have been here. So all I need to do is position the double bond and show the hydrogens. For me, I always prefer to show the hydrogens so that it can make it easier for me to see it properly. So remember, this is going to be position the hydrogens here. Take away take away this part here. Let me use a different color. Cut off that part. Position the double bond here, and the structure is going to be as it should be. So it should be as you can see here. The double bond in between, and then the different hydrogens without any other linking bonds like that. So this is kind of an alkene, or it had a carbon-carbon double bond in it. So the structure should be this one here. As you can see, there is a hydrogen here. There should be a hydrogen here, a hydrogen there, a hydrogen here, and then the rest of the structure as this part here shows. The answer should be that. Let's continue to the next part, question 15. Question 15 says, the repeat unit of a polymer is shown. So here they showed us a repeat unit, and they say this polymer could be, okay, let me first take it away. So they're asking this polymer, and you can look, sometimes you can use the elimination method to rule out. This polymer is formed between, as you can see, this part here is from the carboxylic acid group, and that part here is from an amine group. It looks like it is from dicarboxylic acid and the diamine, or it could be diacyl chloride and the diamine. So we couldn't tell because there is no OH. So here I can say this is a polyamide. It is not a polypeptide because a polypeptide should be formed out of amino acids. So it should be this from amino acids. Let me just write it here. And this part. So polypeptides are part of polyamides, but it's completely different. When you say a polyamide, it should be strictly not just amino acids, although they also have the amide in them. So here, I think for you guys to see extra explanation, I said, because it's made out of a dicarboxylic acid or diacyl chloride and a diamine, it forms a polyamide. To form a polypeptide, the monomers must be amino acids. So for this to be formed, we need amino acids. For this, it could be just a dicarboxylic acid diamine, or it could be a diacyl chloride and a diamine. So question 16 says, the structure of a hydrocarbon is shown. How many peaks will there be in the carbon-13 NMR? So I always advise students to put the carbons because it makes it easier for you to visualize. So if you can see this carbon and that carbon are identical because their neighborhood is exactly the same. So that and that can be carbon 1. This is unique, carbon 2. Then that and that are same, carbon 3, that and that, 4, and that is the 5th. So we can see we have 5 different carbon-13 NMR peaks, and that would be the answer is B. So let's continue on to question 17. Question 17. When a sample of a hydrocarbon is burned completely in oxygen, 2.64 grams of carbon dioxide and 0.81 gram of water are formed. Which of these could be the molecular formula of the hydrocarbon? So here we have to begin, because they've given us the mass of carbon dioxide and the mass of water, we need to find the mass of carbon in the carbon dioxide and the mass of hydrogen in the water. So I began by saying mass of carbon should be 12 divided by 44 times the mass given here. Remember, in CO2, let me draw it here, CO2 we have, this is 12, and the oxygen is going to be 32. So of the total 44, carbon counts for 12. So 12 over 44 times the mass of carbon. And in water, hydrogen counts for 2 out of the total, which is 18. So times the mass of water, which is 0.81. As you can see here and that is how I got 0.72 grams and 0.09 grams. So then I will find my empirical formula by getting the number of moles. So the mass of carbon divided by the atomic mass and the mass of hydrogen divided by atomic mass gives me that as the number of moles. Then I use the number of moles to find the mole ratio, which is 1 to 1.5. Remember, the mole ratio has to be a whole number ratio. So I multiply by 2 to create the simplest whole number ratio, which is going to be a 2 to 3. Now, when I do a 2 to 3, it means the structure should be carbon 2 and hydrogen 3. However, there is no molecule similar to that yet. They've told us molecular formula. So when I multiply this by 2, I can choose any multiple that satisfies from one of the answers. So the only possible multiple is a C, which is carbon 4, hydrogen 6. That is why I chose it as the answer. So let's go to question 18, which is the last question in this section A video. So they said benzene carboxylic acid may be produced from benzene in a two-step process. Here they've given you this part. So we have basically look at all the flow pathway for the production of benzene carboxylic acid. Then they say 8.2 grams of benzene carboxylic acid was formed in this synthesis. This tells you this is kind of the actual mass that was generated. Then they ask what mass of benzene was used. So I'm going to work from using the percentage yield as well as the mass and work backwards. So I began by looking at the actual moles of benzene carboxylic acid produced. Since they've told us this is the actual mass, I can work and find the actual moles, which will be mass over molar mass, which gives us that. Since I know the actual moles and I know the yield, I can be able to find the theoretical yield. So I know that percentage yield is equal to actual yield divided by theoretical yield times 100. So I will get a theoretical yield by making X the subject, and it gives me that theoretical yield. Then I will use it to find the moles based on the equation. So based on the equation, if the theoretical yield of this is going to be 0.11256.8 mole, remember this is in terms of mole, theoretical moles. Looking at the equation, the mole ratio is 1 to 1. It means also the moles, theoretical moles of this should be that. So I'm going to use this percentage yield to be able to find the theoretical yield, basically to find other moles. So here in the second part of this calculation, I said moles of methylbenzene are going to be that, based on the fact that the mole ratio of methylbenzene to benzene carboxylic acid is 1 to 1. Then I came to the percentage yield. So 45% is it's going to be 45. It's equal to, this is going to be the actual divided by the theoretical I'm looking for. Remember, times 100. This is fitting into the percentage yield equation. When I made Y the subject, I got this. It means the moles we're looking for are 0.250151798, 179 I didn't round off. So it means the moles of this, based on the equation, which is mole ratio, which is 1 to 1, the moles of this are going to be 0.250151799. So I came to my final calculation down here. As you can see, the moles of benzene are similar to the moles calculated previously here because of the ratio 1 to 1. Now that I have the moles and I have the molar mass, I can be able to calculate the mass of benzene. Mass of benzene should be the moles of benzene times the molar mass of benzene, which is 19.511. And this is going to be the closest answer. So rounding off to 19.51 grams, the answer should be a C. So I hope you guys understood this. Thank you for being with us. This was the end of the section A paper. Please do not forget to subscribe to our channel. I will keep uploading more videos calculating doing various past papers, as well as discussing various topics in chemistry, biology, as well as math. So please do not forget, I am putting the link to section section C, as well as section B of this video in the description box. Please look below the video. In the description box, you'll be able to find the links to those videos. I'll see you next time. Thank you for being with us.